Okay. Now, let's solve a similar problem. Let's say that I have an inclined plane with some angle theta, and I am sending a mass m with initial velocity v initial. And let's also say that the coefficient of kinetic friction on this surface is mu k. Okay. Now, what kind of motion do we expect? We expect this mass to go up the inclined plane with its initial velocity, but it's going to stop somewhere. And depending on the angle and friction coefficient, it may go back or not. What I would like to find out is how long would it take, or how much of a distance would this travel on the inclined plane, okay, before it comes to a momentary stop. So v is equal to 0 here. That's very similar to your exam question. So let's solve it from a different perspective. Let's solve it using work energy theorem. Now, here's the thing. What is the initial kinetic energy? Let's find out. Well, the initial kinetic energy of this object is 1/2 m v initial square. What's the final kinetic energy? Final kinetic energy is 0. So delta k is minus 1/2 m v initial square. Now, what are the forces acting on my mass? Throughout this motion, I actually have three constant forces acting on my mass. What are those forces? Well, I know that I will have mg acting on. I'll also have a normal force, which is again going to be a constant, and I'll have a friction force. Let's call this a friction. So I want to find out the work done by all these three forces. So let's say I can say this is the work done by gravitational force plus work done by friction force plus work done by the normal force. Now, what was the definition of work? Our more general definition was F dot dl. If I have a constant force, F is a constant, I can take F outside the integral. Then, so for constant F, this turns into F dot d, right? So what's the displacement vector throughout this motion? Here is my displacement vector d. Let's calculate the simplest thing. What is work done by the normal force? It's going to be n dot d. But which way is n acting throughout? It's actually acting perpendicular to my displacement. So what's n dot d? This is 0 as n is perpendicular to d vector. How about the work done by constant friction force? Constant friction force is just opposite, pointing in the opposite direction to my displacement. So this is going to be what? This is going to be minus, well, let's first write the definition. It's going to be F friction dot d, but in terms of magnitude, this is just going to be minus F friction times d, because they are in the opposite directions. How about work done by gravity? It's going to be mg dot d. So g is making an angle like this. How do I calculate mg dot d? Let's see, is it cosine theta or it's the cosine theta between the two vectors, right? So this is basically the angle I need to calculate if I call this phi. But phi is apparently what? This is theta. Phi is pi over 2 plus theta. So mg dot d is m times g times d times cosine pi over 2 plus theta, which is minus sine theta, right? So all in all, the work done is minus mg d sine theta minus F friction d, and that's it. There is an easier way to think about this calculation. Against the friction force, how much net distance did I travel? D. Against the gravitational force, how much net distance did I travel? This is going to be d sine theta. So mg dot d sine theta, I have actually traveled a net distance of d sine theta opposite to the direction of gravity. Okay? Good. So this, what was my delta k? Delta k was minus 1/2 m v initial square. That's going to be minus mg sine theta minus F friction times d. But this is kinetic friction, so can you tell me what's the magnitude of F friction? It's going to be mu k times n. N is equal to mg cosine theta, so it's going to be mu k mg cosine theta. Let's write it here. Overall 1/2 m vi square is minus mg sine theta plus mu k mg cosine theta times d. M's cancel, overall minus sine cancels. So v initial square 1/2 is g times d times sine theta plus mu k cosine theta. And d is vi square over 2g sine theta plus mu k cosine theta. Did I reach my goal? My goal was to find the length traveled on the inclined plane. So that's great. I reached my goal. How about the units? Vi square is meter square per second square. 2 doesn't have units. G is meter per second square. Sine theta plus mu k cosine theta doesn't have any units. So this is meters, the units. Check. How about some limits? What would that distance be if vi is 0? If I'm not pushing the object, it will just stay there. That's right, d. So vi goes to 0, d goes to 0, checks. How about a frictionless plane? What would I expect? I would expect a longer distance, so it's good that I have mu k in the denominator, right? That's another thing. But here is the thing. That is actually easier than the solution in the exam, right? Where you were not supposed to use the work energy theorem. But that ease came at a cost. What's the cost here? And what have we lost? We have lost some information. We have lost the information about time. If I actually ask you how long would it take for this mass to momentarily stop, then I wouldn't be able to answer that question using work energy theorem. So essentially, when I actually start dealing with energy, I lose the information about how long any process takes. Okay? So if a question asks you to find the time to do something, you will not be able to do that just by work energy theorem. All right? Comment. Louder. That's a general thing. In quantum mechanics, you'll see that this is called energy-time uncertainty relation. And you have to learn a lot of stuff before you get there. So let's talk about other things. Let's talk about projectile motion. So if I'm actually throwing an object vi with velocity vi, which has mass m, with an angle theta, I would like to calculate two things. First, I'd like to calculate what's the maximum height it actually reaches. The second thing is I would like to calculate what's the final velocity it has. Once in flight, what is the only force acting on this object? It's going to be its weight. It's going to be mg, right? So work energy theorem, let's use that work energy theorem to find the final velocity, final speed. Delta k is 1/2 mv final square minus 1/2 mv initial square. That is equal to, now my force is constant, that's equal to work. I can say it's F dot dl over this whole path. But a constant, for a constant force, this is just going to be F times the distance traveled. And F is mg. No, it's mg. A vector is mg. But what's the displacement vector through this motion? The displacement vector is like this. Mg is, so one is horizontal, the other is vertical. Mg dot d is 0. Which means the change in kinetic energy is 0. Which basically tells me that V initial square is V final square. So V final is equal to V initial. Good. How about this maximum height? How can I find it? Well, here I have to be a little bit more smart. What will the velocity of this object look like at the top? It's going to be exactly horizontal, right? And that horizontal velocity, does it change throughout the motion? No, it doesn't. Motion in the x direction was motion with constant velocity. So its velocity will be vi cosine theta. So initial kinetic energy is 1/2 mvi square. The kinetic energy at the top, kT, is 1/2 mvi square cosine square theta. So what does the work energy theorem tell me? Okay, maybe not. The work energy theorem tells me that k top minus k initial is F gravity times d. And what's the d vector from my initial point to the final point. That will be my d vector. mg dot d. mg is down. So what's the distance traveled opposite of mg? It's going to be the angle here. It's going to be exactly h. So it's going to be mg times h with a minus sign. Is the logic clear here? Let me do it again. So I would like to calculate d dot mg. And I will say, hey, this is d dot mg is in the triangle. This angle is not theta, it's phi, it's a different angle. D is the vector which forms the hypotenuse of a right triangle, and the distance traveled opposite to g is exactly h. So it's going to be minus mgh. So let's write everything down. I have 1/2 m vi square cosine square theta minus 1 is mgh with a minus sign. M's cancelled. Or h is vi square over 2g 1 minus cosine square theta. So h is vi sine theta square over 2g. Now, I could have very easily found both of these answers by writing my dynamical equations. Motion in x is motion with constant velocity, motion in y is motion with constant acceleration. I could have found both of them. But here, I've actually found the answers with less calculation. What did I lose? With work energy theorem, I will not be able to tell you how long it would take to hit the ground again, or how long it would take to reach the top point. Okay. Another comment. Be very careful. Kinetic energy is a scalar, which was a fancy word for number, right? It's just a number. It doesn't have a direction. Okay. So saying that kinetic energy in the x direction is conserved is not right. That would actually lead to some pretty terrible results. Okay. If you keep thinking about kinetic energy as a vectorial quantity, it's not a vectorial quantity. Okay. So, but here is one more thing. Maybe I'm doing too much of a job. Every time I have this motion, whether along a inclined plane or free motion, or maybe motion on some strange path, I keep calculating the work done by gravity. The work done by gravity at the end of the day, because although it's initial point to final point, F dot dl. So your object may be traveling in a strange path. At the end of the day, because F is constant, it's just mg, a constant can be taken outside the integral, right? So it's going to be mg dot integral dl from your initial point to your final point. What's the integral dl from initial point to final point? That's basically summation of all these small vectors. Summation of all these small vectors give you just a big vector from the initial point to the final point. That's your full displacement vector. So this is going to be d. Okay? That's the meaning of the line integral. That's the simplest line integral we can do. Okay? So work done by gravity is apparently always mg dot d. Or maybe I can write it in another word. In other words, if this is the direction of g, the work done by gravity is essentially something related to the height of the object. That's the total distance traveled opposite to g. So it's going to be minus mgh in all situations. So what was my initial work energy theorem? I said my change in kinetic energy is the total work done on my object. But now I'll say, hey, my kinetic energy is work done by gravity plus work done by all other forces. And I've just calculated this to be minus mgh. And with a great trick, I'll just take a minus mgh to the other side. I'll say delta k plus mgh is work done by other forces. And I'll even write this in another form. I'll say, hey, this was 1/2 mv final square. And I'll write plus mgh final minus 1/2 mv initial square plus mgh initial height and final height is equal to work done by all the forces except gravity. So this is sort of another kind of work energy theorem. Instead of just thinking about kinetic energy, now I'll say, hey, there's kinetic energy plus another source of energy, which is coming from gravitation. So I'll call this UG, which is going to m times g times h of the object. I'll call this as gravitational potential energy. So what's my new object? I'll call this total mechanical energy, kinetic plus gravitational potential energy. The change in my total energy is work done by all other forces other than gravity. Now, you may say, hey, why not do it the same thing for other forces, right? For example, if there are forces like, say, a constant electric field applied on a charged object, I'll basically, for any constant force, I'll be able to do this, right? I can take it, instead of thinking of the work done by this force, I can basically take it to the other side of the equation and think of it as if it's a part of energy. Okay? So some potential energy related to this force. So the question is, can we define a potential energy for the other forces as well? And here's the thing. It depends, obviously, on the nature of the force. My general formula for work was F dot dl. Okay. In my previous calculation for gravity, it just turned out this is equal to minus mg h final minus h initial. So basically this was minus gravitational potential at the final point, ug final, minus ug initial. But that was a pretty special case. In general, this work from some initial point to final point may depend on what kind of path you have taken. For gravitational potential for gravitational forces, we've seen that even if you go through path 1 or path 2 or path 3, gravitational force, gravitational work was path independent. For example, if I started from some height, I did some crazy motion, I don't know what else, and came back to the same point, what would be the work done by gravitational force? It would be 0. To show such a crazy scenario, we say if I integrate F dot dl, gravitational, on a closed path. So when I put a small circle onto a integral, says it starts from the same point and comes back to the same point. For a gravitational force, this is 0. It turns out if for any potential or if any force, for any force, if F dot dl is 0, a potential energy can be defined. So basically what I would like to, if I am able to make sure that when I come back to the same point, I have basically 0 work done by such a force, then it's okay. I can define a potential energy associated with that. Let me first show you a counterexample. The kind of force for which we cannot define a potential. And it's our old friend friction. Let's say that there is a friction here. There's some kinetic force. I take my mass, I move it very slowly to the right, and then turn back and move it to the left to the same point. When I'm moving to the right, my force is opposing the motion. So V dot F is negative when I'm going to the right. When I'm going to the left, when I actually reverse the direction, now force is also reversed this direction. So V dot F is always negative, which means integral F friction dot dl has always the same sign. It always has a negative sign. So it's less than 0. It's actually not equal to 0. Basically what I'm saying is that if I take an object on a frictionful surface, a surface with friction, if I move it one way and come back, I have dissipated some energy. Of course I have dissipated some energy. That's intuitively obvious to you. You've heard the sound. That sound actually tells you something. Some energy is lost into sound, some of my mechanical energy. For such a force, so friction is path dependent, which means it is a force for which no potential can be defined. So you cannot talk about a frictional potential. Okay? No potential possible. And that is called a non-conservative. Or sometimes also called dissipative force. But let's talk about another force we have just learned. How about the force applied by a spring? The force applied by a spring is quite easy. It only depends on how much compression or stretching you have. If I compress this object, while I'm compressing, I'm actually seeing the force opposing my motion. But when I'm actually going back, my velocity is this way. The force is actually encouraging motion in that direction, right? So V dot F changes sign. It changes sign exactly at each point. The sign is determined by the sign of V. So it means that if I actually come back to the same point, F dot dl must equally be 0, because on my path I crossed each point twice, and each point had different values for f dot v, exactly opposite values, which will cancel when I carry out the integral. So this is a conservative force, which means I can define a potential energy for a spring. Okay. So what would be my potential energy for a spring? U spring. We have calculated the work done by a spring. It was minus 1/2 k x square. So it's going to be, I'm taking it to the other side of the equation. My potential energy would be 1/2 k times x square. X is compression or stretching. So here is what my work energy theorem looks like. Okay. Here I'll define a new concept, the total energy, or I'll call this mechanical energy. What do I have in here? I have the kinetic energy, plus I have the potential energy due to gravitation. I may have the potential energy of if there are any compressed springs in the system, plus all the potentials due to conservative forces. Now my work energy theorem tells me that delta E, the change in mechanical energy, is just work done by non-conservative forces. Okay, not even external forces, non-conservative forces. Now, this is really good. It tells me that, well, practically for Physics 101, it tells me that mechanical energy is mostly lost to friction, either air friction or surface friction. But here is something more interesting. I told you that all forces in nature come from 4 fundamental sources: gravity, electromagnetic interaction, weak and strong nuclear forces. As far as we know, all these 4 forces are conservative. So you can actually define potential energies regarding all these forces, which somehow tells us that there is this concept of energy which is conserved in nature. But that energy comes from very different sources. What's happening here when I'm actually moving an object on a frictionless, on a plane with friction? I have my kinetic energy, I have my gravitational potential energy, and some of that energy is turned into heat. But what is heat? When you think actually more deeply, heat is just the motion of the molecules at the surface and basically inside this object. So if I took that into account, the total energy would be conserved. So what we call lost energy is actually the energy we are not accounting for. Okay? So when I talk about dissipation, I'm talking about energy in a form that I cannot retrieve or I cannot define. So actually energy if you look at the totality of the system, we believe energy is conserved. Now, how much of a fundamental thing is this? I mean, we say energy is conserved through nature. Is that a very fundamental principle? I mean, you may say, yes, it's extremely fundamental in all reactions we know of. In chemistry, you can think of the most violent reaction, like a TNT blowing up. Energy is still conserved there. I can have even more violent reactions than chemistry. I can have nuclear reactions. I can even have a star blowing up, a supernova. And so far as we know, energy is conserved. But here, let's be very careful. What I did is I actually defined, I increased the definition of my energy. I started my kinetic energy. I added to it my gravitational potential. Then I added to it my spring potential. Okay. In physics 102, you'll actually put in electrostatic potential to that. Okay. Then you will actually put some magnetic potential to that. Okay. So on one hand, it's actually important that there is this total overall conserved quantity. On the other hand, it's a bit of a gimmick. We're just naming new things and adding to this thing we called energy. Yes, comment. That's okay. I mean, so here is the thing. Whenever when you actually do an experiment and see that energy is not conserved, you immediately look for a source which explains that lost energy. For example, neutrinos were found like that. Neutrino particles, people said either energy was not conserved or something else was happening. And neutrino turns out it's a horribly hard particle to observe. It took 50 years to build a detector to find that particle. But still, there is a deeper reason why total energy is conserved as far as we know. And that's again a comment for the physicists in class. It turns out time translational invariance. For example, all our equations do not have a concept of absolute time. They do not start from, f is equal to ma at t equals to 0, f equals ma at t equals 1 hour, 3 hours. We believe f is going to equal to ma in 1,000 years. Okay, that's called time translational invariance. Your rules do not depend on which time they are applied. There's a very fantastic mathematician called Emil Noether, and she proved that time translation invariance causes energy conservation. So it's actually, there's a very nice mathematical reason behind that. That's called Noether's theorem. I would urge you to look it up. You'll not understand anything at this stage, but it's at least good to know that energy conservation can be understood more deeply. Okay? Good. So let's actually solve a problem. Okay? So an object of mass m is dropped on a spring constant k. So let's say this distance is h. So what do I expect? I expect when the object is dropped, it's going to compress the spring by a amount delta. So let's call delta the maximum compression of the spring. So basically, I would like to find what delta is if, my gravitational acceleration is g. And initially, I'm just basically being me, dropping this mass without any initial velocity. How do I solve this? Obviously, we are talking about conservation of energy. But can you tell me what's the initial mechanical energy? That's it. Initially, do I have any kinetic energy? No. Do I have any spring potential energy? No, it's not. It's uncompressed. So all the energy is coming from the potential energy. But here's the thing. Where do I measure the potential energy from? Should I measure it always from the sea level? Should I measure it from the bottom of the Mariana Trench, from the deepest point in the ocean? Should I measure it from the top of Everest? And here's a very excellent response to that. It does not matter. Let's see why it does not matter. I will measure it. I'll choose this to be my reference level. And then I have a bit of a problem. I do not know what's the relaxed length of the spring. I'll call this L0. So what is my initial potential energy in that situation? It's going to be mgh plus L0. How about my final energy? What is the kinetic energy at the moment of maximum compression? It's 0, right? Velocity is 0. At a moment later, it will actually start its motion up. So kinetic energy is 0. What is the spring potential energy? So we've just said it's 1/2 k times the compression squared. How about the gravitational potential energy? It's going to be plus mg. So if this full distance is L0, this is L0 minus delta. Are there any non-conservative forces in this problem? Maybe there is air friction, but I certainly neglect that. No? Okay. So if there are no non-conservative forces, initial energy must be equal to the final energy. Let's actually do that. Initial energy is mgh plus mgl0. Final energy is 1/2 k delta square plus mgl0 minus mg delta. Hey, mgl0s cancelled, and that's not by accident. It turns out it really doesn't matter what you choose your ground level, what you choose as your reference level. So mgh is height with respect to some fixed level. As long as you keep it fixed throughout the problem, it's not going to change your answer. All right? Good. So let's solve this. mgh is 1/2 k delta square minus mg delta. I'll write this as follows. This is going to be k over 2 delta square minus mg delta minus mgh. So what are my solutions? Minus b over 2a is k, plus minus 1 over 2a is k, square root of b square is m square g square, minus 4a is k over 2, c is minus mgh. mg over k plus minus square root mg over k squared plus 2 mg over k times h. Which root should I take? Plus root or minus root? The way I defined delta, do I expect it to be positive or negative? Positive, right? I actually expressed it as the compression, how much compression I had in the spring. So it should be a positive amount. Now, which of these terms is larger, mg over k or square root of mg over k square plus? The second term is larger because if this is mg over k, the second one is the hypotenuse of a triangle with some positive quantity here. So the hypotenuse is always larger than one of the sides, right? So which root do I take? I take the plus root. Let's see. Delta is mg over k minus. Let's see. Did I reach my goal? Yes. I'll not check the units. The units are fine. Okay. The problem is, let's look at the limits. What would you expect this delta to be if h is 0, if I'm actually acting it as dropping this object from 0 height? What should be the maximum compression? Let's think about it. If I'm dropping it from 0, what will happen? It will actually get some compression due to the weight of this object, right? So what would be the change? This is delta. Here, mg times delta would be 1/2 mg, 1/2, k, delta square. So delta would be 2 mg divided by k. Do I get that result here if h is 0? Yes, I do get that same result. So please check the units yourself. This is the correct result. Okay? I'll see you in 3 days.